Almost 50 years ago, humans built a small machine and threw it into space. It wasn't meant to be famous. It wasn't meant to last long. It was meant to do one simple job: fly past a couple of planets, take some pictures, and then quietly go dark. That machine is called Voyager 1, and instead of dying on schedule, it just kept going. Today, Voyager 1 is still awake, still listening, still talking back to Earth from a place so far away that our own sun looks like just another star in its sky. It has outlived almost every engineer who built it, every prediction that was made about it, and every reasonable expectation anyone had for its short little mission. So how did a spacecraft built in the 1970s, with less computing power than a cheap calculator, end up becoming humanity's furthest and longest-running messenger? That's the story we're going to tell, from the day it launched to the strange and almost unbelievable future waiting for it. A future measured not in years, but in trillions of years. Let's rewind to the beginning. In 1977, NASA had a rare opportunity. Once every couple hundred years, the outer planets of our solar system line up in just the right way, so a single spacecraft can visit several of them in one trip, using each planet's gravity like a slingshot to boost its speed. Miss that window and you'd need separate missions, decades apart, to see the same planets. NASA didn't miss it. They built two spacecraft, Voyager 1 and Voyager 2, and launched them weeks apart to take advantage of that rare planetary lineup. Voyager 1 wasn't just carrying cameras and science instruments, though. Bolted to its side was something almost poetic, a gold-coated record disc packed with sounds and images from Earth. Birdsong, laughter, a human heartbeat, music from dozens of cultures, greetings spoken in many different languages, a diagram showing how to find our sun in case anything or anyone ever found the record floating out there. It wasn't science, it was a message in a bottle, tossed into the biggest ocean there is. Nobody expected it to be found, but nobody wanted to skip the chance to send it either. From day one, there was no plan to bring Voyager 1 home. It wasn't a round trip. It was built to survive freezing cold, punishing radiation, and total isolation for as long as it took to finish its job, and then just keep flying forever, as far as physics would allow. At launch, as long as it took was expected to mean 4 or 5 years, just enough time to swing past Jupiter and Saturn. Nobody on that launch pad in 1977 imagined that same spacecraft would still be sending signals back to Earth nearly 50 years later, from a distance no human object had ever reached before. And yet, here we are. In the next part, we follow Voyager 1 to its first major stop, Jupiter, where it stumbles onto one of the biggest surprises in the history of space exploration on a small moon nobody expected to be interesting at all. Because the story of Voyager 1 isn't really about a machine. It's about how something built for a short, simple job can end up doing something nobody ever planned for, and just keep going, long after everyone stopped expecting it to. Stick around, because this trip only gets stranger from here, all the way out to a future so distant the numbers barely make sense anymore. By 1979, 2 years into its journey, Voyager 1 reaches Jupiter, the biggest planet in our solar system and one of the most violent. Its cameras capture storms bigger than entire planets, winds tearing across the cloud tops at over 1,500 kilometers per hour. And right in the middle of it all, the Great Red Spot, a storm so massive that the entire planet Earth could fit inside it with room to spare. That alone would have made the flyby historic. But the real shock didn't come from Jupiter itself. It came from one of its moons. As Voyager 1 passes close to Io, scientists notice something nobody expected to see: active volcanoes erupting in real time on a small rocky moon hundreds of millions of kilometers from the sun. Some of the eruptions shoot plumes of material over 100 kilometers into the sky, visible even to a spacecraft just passing by. This one discovery quietly rewrote what scientists thought they knew about small, cold worlds. Before this flyby, the assumption was simple. A moon that small, that far from the sun's warmth, should have cooled down and gone quiet billions of years ago, the same way our own moon has. Instead, Io turned out to be the most volcanically active place in the entire solar system. The reason turned out to be almost as strange as the discovery itself. Io doesn't get its heat from the sun. It gets squeezed. Jupiter's massive gravity, combined with the pull of its other large moons, constantly stretches and flexes Io's interior, like squeezing a rubber ball over and over. That friction generates enough heat to keep the volcanoes erupting, even after billions of years, with no sunlight required at all. It was proof that a world doesn't need to be warm and sunny to be alive with activity. Sometimes gravity alone is enough. Voyager also turns its instruments toward 3 of Jupiter's other big moons. Europa looks smooth and strangely bright, its surface crossed with dark cracks that hint at something shifting underneath. Ganymede shows a complicated, varied landscape. Callisto looks old and worn, covered in craters from billions of years of impacts. And there's a part of Jupiter you can't see in any photo: its magnetic field. Jupiter's magnetosphere is enormous, trapping charged particles into radiation belts far more intense than anything Earth has. Voyager flies straight through part of this invisible danger zone, measuring radiation strong enough to fry sensitive electronics, and somehow keeps working. Once the flyby is done, Jupiter gives Voyager exactly what it needs to keep moving. As the spacecraft swings past the planet, it borrows a small amount of Jupiter's own orbital energy, a maneuver called a gravity assist, and uses that stolen energy to pick up extra speed, bending its path further out into the solar system. Jupiter wasn't just a stop, it was a launch pad for the next leg of the journey. Next stop, Saturn, a planet famous for its rings. But the biggest discovery there won't be about the rings at all. It'll be about one of its moons, a place so strange that scientists are still trying to fully understand it decades later. In the next part, we follow Voyager 1 into the golden light of Saturn, and to a moon that might be one of the strangest places in the entire solar system. By 1980, Voyager 1 arrives at Saturn, a pale gold planet wrapped in rings that, from Earth, look like one smooth glowing band. Up close, it's a completely different picture. Voyager reveals that Saturn's rings aren't smooth at all. They're made of countless individual ringlets, gaps, and sharp edges, shaped by the gravity of Saturn itself and the many moons orbiting nearby. The rings are made mostly of water ice, in pieces ranging from tiny grains of dust to boulders, stretched across hundreds of thousands of kilometers of space. Some of Saturn's smaller moons act almost like invisible sculptors, keeping certain rings neatly shaped and carving clean gaps between others. It's one of the most delicate, oddly beautiful systems in the entire solar system. But the real star of this flyby isn't the rings. It's a moon called Titan. Titan is bigger than the planet Mercury, and it's wrapped in something no other moon in our solar system has. A thick, dense atmosphere, so heavy that it completely hides the surface underneath. That atmosphere is made mostly of nitrogen, mixed with methane and other complex chemicals, and the pressure at Titan's surface is actually higher than the pressure here on Earth. To scientists, that thick atmosphere is like a live chemistry experiment happening in real time. Sunlight and energetic particles constantly break down molecules in the sky, and those broken pieces recombine into heavier, stranger compounds. In the extreme cold of the outer solar system, those compounds form hazes, methane rain, and deposits that settle onto the ground below. Voyager 1's flyby only gets a brief look, but decades later, other missions would confirm just how bizarre Titan really is. A world with rivers, lakes, and seas, not made of water, but of liquid methane and ethane, along with dunes made of frozen organic material stretching across the landscape. It's one of the strangest and most alien places we've ever gotten a close look at, and Voyager 1 was the first spacecraft to ever get near it. As Voyager passes close to Titan, its path bends sharply, and this time, the bend isn't just aiming it at another planet. This trajectory change sends Voyager 1 on a path that will eventually take it completely out of the solar system. From this point on, there are no more planets to visit, no more flybys planned. Just a long, quiet journey outward, into territory no human-made object had ever explored before. 10 years later, in 1990, something unexpected happens. A member of Voyager's science team convinces the mission to turn the spacecraft's camera around one final time and look back toward home. From a distance of nearly 6 billion kilometers, Voyager 1 captures a photo that will later become one of the most famous images ever taken in the history of space exploration. A single frame showing several planets of our solar system at once, with Earth appearing as nothing more than a tiny, pale point of light caught inside a beam of scattered sunlight. Every person who has ever lived, every memory, every moment in human history, all of it happened on that one small dot. In the next part, we look closer at that photograph, why it almost didn't happen, and what it changed about the way people think about our place in the universe. In February of 1990, Voyager 1 is nearly 6 billion kilometers from home. Its main scientific mission is long finished. There are no more planets to study, no more rings or moons waiting to be photographed for the first time. By all logic, it's time to shut the cameras off for good and save whatever power is left. But before that happens, one member of the mission's science team pushes for something different. He wants Voyager to turn its camera around one last time and look back at the solar system it's leaving behind. It wasn't an easy sell. Pointing Voyager's delicate camera anywhere near the direction of the sun risked permanently damaging the equipment with glare. The team had to calculate the angle with real precision, carefully avoiding the sun's brightest light, while still capturing the planets scattered around it. They pulled it off. The result is a series of images now known as the family portrait, a wide mosaic showing several planets of our solar system in a single frame, photographed from farther away than any spacecraft had ever looked back from before. In one of those frames, Earth appears as a single pale dot, barely a pixel wide, suspended inside a stray beam of sunlight. That's it. That's home. Every person who has ever been born, every war, every love story, every quiet, ordinary Tuesday, all of it happened on that one small, fragile point of light. This photo was never part of the original mission plan. It only exists because someone on the team believed people deserved to see themselves from that kind of distance, at least once. Small, alone, and precious, floating in the dark. Shortly after taking this image, Voyager's cameras are switched off permanently to conserve its shrinking power supply. There would be no more pictures after this. From here on, Voyager 1 becomes something different. Not an explorer taking photos, but a quiet messenger, moving forward in silence, sending back only numbers and signals instead of images. The spacecraft continues outward at a steady pace of about 17 kilometers every second, fast enough to cross the distance between New York and Los Angeles in under 4 minutes. Ahead of it lies one more major boundary, the heliopause. This is the invisible line where the outward push of our sun's solar wind is finally balanced out by the thin material drifting between other star systems. The actual edge of our solar system's influence. Crossing that boundary isn't like driving past a sign on a highway. There's no dramatic flash, no visible marker. Voyager only detects it indirectly through subtle shifts in the particles surrounding it. A sudden drop in particles that originate from our own sun, paired with a rise in cosmic rays arriving from deep space. Scientists had debated for years exactly where this boundary would be and what crossing it would even look like in the data. Some expected a sharp, sudden transition. Others expected a slow, blurry shift over a longer stretch of space. In the next part, we find out who was right, and the exact moment Voyager 1 became the first human-made object to ever leave the solar system entirely. For years, scientists could only guess where the true edge of our solar system actually was. They knew it existed, the point where the outward push of our sun's solar wind finally gives way to the thin material drifting between stars. But nobody had ever measured it directly, because nothing built by humans had ever traveled far enough to reach it. As Voyager 1 creeps closer to this boundary, called the heliopause, its instruments start to pick up on changes. The particles surrounding the spacecraft begin shifting. Voyager's detectors register a sharp drop in particles that originate from inside our own solar system, paired with a sudden rise in cosmic rays streaming in from far beyond it. It wasn't a single dramatic jump. It was a gradual shift, one measurement at a time, as the spacecraft crossed from a region shaped by our sun into a region shaped by everything else, the vast space between stars. On August 25th, 2012, Voyager 1 officially crosses the heliopause and enters interstellar space. It becomes the very first human-made object to ever leave the region of space dominated by our sun and travel into the space between individual star systems. This single moment settled a scientific debate that had been going on for years. Researchers finally had real, direct measurements of what conditions actually look like just outside our solar system. Information that had previously existed only as theory and prediction, which brings the story to now. As of 2026, Voyager 1 is approaching another remarkable milestone. Later this year, it's expected to become the first human-made object ever to reach a distance of one full light day from Earth, roughly 25.9 billion kilometers away. To put that in perspective, light itself, moving at nearly 300,000 kilometers every second, takes a full 24 hours to cover that distance. Send a signal to Voyager on a Monday morning, and you won't hear anything back until Wednesday. Every single exchange with this tiny, aging spacecraft now takes 2 full days round trip. A command sent, a long silent wait, and then, if everything goes right, a reply. It's a strange thing to sit with. This same spacecraft, back when it was flying past Jupiter and Saturn decades ago, used to send back pictures and readings within minutes. Now, a simple hello takes 48 hours for a reply. Meanwhile, Voyager's power supply keeps shrinking every single year. Its onboard generators convert heat from slowly decaying radioactive material into electricity. But that heat naturally fades with time, and engineers estimate the spacecraft loses a small amount of usable power every year without fail. To stretch what little power remains, mission engineers on Earth have had to make hard choices, shutting down one instrument after another, keeping only what matters most still running. In the next part, we look at what happens next, not just in the coming years, but the coming decades, as Voyager 1 slowly goes quiet for good. Right now, in 2026, Voyager 1 is still talking to Earth. Barely. Only a couple of its original instruments are still running. Everything else has been shut down over the years, one system at a time, as engineers fight to stretch a power supply that keeps shrinking no matter what they do. The power comes from a radioactive heat source slowly decaying inside the spacecraft. It can't be recharged, it can't be replaced. It simply runs down a little more every year, the same way a battery slowly drains even when nothing is using it. Engineers already know how this part of the story ends. Sometime in the coming years, likely before the 2030s are over, Voyager 1 will lose enough power that it can no longer keep even its most basic systems running. At that point, the spacecraft will stop transmitting data entirely. No dramatic final message. No last transmission announcing the end. Just silence, one day, where there used to be a faint signal. But here's the part that's almost impossible to fully picture. Voyager 1 doesn't stop moving just because it stops talking. Once its power runs out and its instruments go dark, the spacecraft becomes something closer to a piece of drifting rock than a machine, except it will keep moving in a straight, predictable path, at roughly 17 kilometers every second, for an unimaginable length of time afterward. There's nothing out in interstellar space to slow it down. No air resistance, no friction, just enormous emptiness stretching in every direction for trillions of kilometers between anything solid enough to interact with. So the silence doesn't mean the end of the journey. It just means the end of us being able to hear about it. Voyager 1 will keep drifting past the position of nearby stars, though nearby here means trillions of kilometers, and passing can take tens of thousands of years for a single encounter. In roughly 40,000 years, it's expected to drift within a light year or so of a star called Gliese 445. Not a close approach by any normal definition, but the closest thing to a landmark this spacecraft will experience for a very long time. After that, there's nothing to do but keep going. No more mission control, no more scientists watching the data, just a small metal object, carrying a golden record full of human sounds and images, sailing silently through the space between stars. Earth, meanwhile, keeps spinning. Generations pass. Technology changes so much that Voyager 1 becomes something closer to a historical artifact than an active mission, the way we might think about ancient explorers today, except this one is still physically out there, moving. In the next part, we start zooming out from human timescales entirely into a future measured not in decades or centuries, but in millions of years, following Voyager 1 as it drifts even further from everything we've ever known. Try to picture a million years. Not $1 million, not 1,000,000 miles, a full million years of time. Human civilization, in its entire recorded history, doesn't even come close to 1,000,000 years old. Yet Voyager 1, moving quietly through the dark at about 17 kilometers every second, will barely have started its real journey by then. By the time 1,000,000 years have passed, Voyager 1 will have drifted many trillions of kilometers from Earth. It will have long since gone silent, its instruments dead, its power supply exhausted for hundreds of thousands of years. There will be no signal, no data, no way for anyone, even if humans still exist, to know exactly where it is or what condition it's in. But it will still be moving. Nothing in interstellar space is stopping it. Stars themselves are also moving, drifting slowly through the galaxy on their own long, slow paths. Over these kinds of timescales, the map of nearby stars that exists today won't even be recognizable. Constellations we know now will have shifted into completely different shapes. Some nearby stars will have moved far away. Others we've never paid attention to will have drifted closer. Voyager 1 will keep threading through this slowly reshuffling galaxy, occasionally passing relatively close to other star systems, though close in interstellar terms can still mean trillions of kilometers of empty space. Somewhere around 300,000 years from now, Voyager 1 is expected to pass near a star system, at a distance still vast by any human standard, but astronomically speaking, a notable moment in its long journey. None of this will be witnessed by anyone. There's no possibility of a signal, no telescope capable of tracking something this small across this kind of distance. From this point forward, Voyager 1's location becomes something closer to a calculation than an observation. Scientists can predict its path using physics and the motion of nearby stars, but nobody can actually check. And this is where the story stops being about human history entirely and starts becoming about something closer to geological or even cosmic history. 1,000,000 years is barely the beginning. Voyager 1's orbit will carry it around the center of our galaxy, following a long, slow loop that takes hundreds of millions of years to complete, much like the Sun's own orbit around the galactic center. By the time we're talking about hundreds of millions of years, entire species on Earth will have evolved and gone extinct multiple times over, purely as a matter of ordinary evolutionary timescales. Continents will have shifted into new shapes, and Voyager 1, this tiny machine built in the 1970s, will still be out there, orbiting the galaxy right alongside our Sun, carrying its golden record into a future that no human will ever get to witness firsthand. In the final part, we go as far as the math allows, past the death of our Sun, past the end of Earth as we know it, and all the way out to a timescale so enormous that the numbers themselves start to lose their meaning. 10 trillion years. Everything has an ending. Stars burn out. Planets get swallowed or frozen. Even our own Sun has an expiration date. In roughly 5 billion years, scientists expect our Sun to run out of the hydrogen fuel that's kept it burning steadily for billions of years. It will swell into a much larger, cooler star, likely engulfing Mercury and Venus, and possibly reaching close enough to make Earth uninhabitable if it hasn't already become so long before that point. Voyager 1 won't be anywhere near home when that happens. By 5 billion years from now, it will have been drifting through interstellar space for a length of time so long that Earth's entire history, from the first single-celled organisms to right now, today, would be a small fraction of it. But Voyager 1 itself won't be destroyed by the sun's death. It'll simply keep orbiting the galaxy, following the same long, slow gravitational path stars take, completing loop after loop around the galactic center, over and over, for an amount of time that becomes difficult to even describe using ordinary numbers. This is where scientists start using timescales that go far beyond anything relevant to human experience. Not just billions of years, but trillions. Around 4 to 5 billion years from now, our galaxy, the Milky Way, is expected to collide and merge with the nearby Andromeda galaxy. Contrary to what that sounds like, actual collisions between stars during this kind of galactic merger are extremely rare, because stars are so far apart from each other, relative to their size, that they mostly just drift past one another as the two galaxies combine into one larger galaxy. Voyager 1 would simply be along for the ride, its orbit reshaped by the merger, continuing to drift through this newly combined galaxy for ages afterward. Now stretch the timeline even further, out to 10 trillion years. At that point, based on current models of how stars form and burn out, the era of new star formation across the universe is expected to have mostly ended. Most stars, including ones far larger and longer lived than our Sun, will have burned through their fuel and faded into dim, cooling remnants. The universe at that point would look far darker and quieter than the busy, star-filled sky we see today. Voyager 1, according to scientists' calculations, would still be intact. In the near-perfect emptiness of interstellar and eventually intergalactic space, there's essentially nothing to collide with, no atmosphere to burn it up, and no significant force to break it apart. Its structure, a small metal frame, a golden record, remnants of instruments long since powered down, could realistically remain physically intact for this entire span of time. It would still be moving, following an orbit shaped by gravity, drifting through a galaxy that would look almost nothing like the one it left behind, under a sky filled with dim, dying stars instead of the crowded night sky we know today. It's an almost impossible thing to sit with. A small machine built by hand in the 1970s, launched to study a couple of planets over the course of a few years, may end up being one of the most durable objects humanity has ever created, outlasting our sun, our planet, and possibly our entire species, while still carrying a small golden record of who we once were, drifting quietly through a universe that's long since moved on without. That's the full arc of Voyager 1. From a launch pad in 1977 to a future so distant that billions of years stops being enough, and only trillions will do.